The purpose of this video is to work through choosing an exposure variable for the model. So let's review where we are. In the last video, I chose my outcome variables, and I chose one which was a continuous measure and one which was a binary measure. For the continuous measure, I chose airway constriction, which is going to be measured by the ratio of FEV1 to FVC. And for the binary measure, I chose chronic obstructive pulmonary disease, abbreviated COPD, and it is either yes or no for each person. Now, I decided that I wanted to use some measure of tobacco smoke exposure as the cause in my model, or the exposure variable. Now, before we dive into looking for an exposure variable, it might be helpful to review the framework in which we're working. So you might remember this diagram from the video called Connecting Our Model to Reality. And remember that these people over here, these represent the people for whom we have data. And we said that if we want to model, for example, tobacco smoke exposure having an effect on some lung outcome, then we need to measure both the tobacco smoke exposure and the lung outcome on every person who is going to be included in our model. And I have chosen two different models. One has a continuous outcome, and so I need to have data on tobacco smoke exposure. I don't yet know how I'm going to construct that, and also airway constriction, the FEV1 to FVC ratio. And for my binary outcome model, I also need some construct of tobacco smoke exposure, and I'll be using COPD as the outcome. Now, you're only going to be required to create one of these types of models. You don't need to create two models. I'm just doing two of them to show the techniques for both types of model. Now let's look at this again to remember what it is we're trying to do. And for this view, it's easier to use the continuous outcome because it is more meaningfully represented in this kind of diagram where we're using a column to represent the value of the variable. And I've taken numbers out here, but each of these dots represents a number that we would have for the each person in our data set. And so what we're going to be doing is we're going to be looking for patterns in the data. And what we'd expect to see with these kind of variables is that we would expect to see that as the tobacco smoke exposure is higher, that we would have a lower FEV1 to FVC ratio because the tobacco smoke exposure is having a causal effect to increase airway constriction. And if we see this kind of pattern that we expect, where the variables are moving against each other, we can then hypothesize one of three causal relationships between the variables. One is that the tobacco smoke is actually having a causal effect on the airway constriction. Another is reverse causality, that the airway constriction is having a causal effect on the tobacco smoke exposure. And a third one is confounding, that there's some other thing which is having a causal effect both on tobacco smoke exposure and on airway constriction. And that is why we see the association between the variables in our data. So the next thing I did was to go to the NHANES data to see what possibilities there were for exposure variables that could represent tobacco smoke exposure. And if you remember, my outcome variables were both measured from the spirometry data, which were collected on individuals between the ages of 6 and 79. So I looked through the data as I did before, and I found a few possibilities that I want to describe here very quickly. The first set of data were from the questionnaire, and they were only collected on individuals between the ages of 20 and 79. The first question was, have you smoked at least 100 cigarettes in your entire lifetime? And it's coded either yes or no. The second was, how old were you when you first started smoking fairly regularly? This one is a number, it's a continuous variable. The third one was, do you now smoke cigarettes? This one was coded yes or no. And the fourth one was, how old were you when you last smoked cigarettes fairly regularly? This one was a number, also a continuous variable. Now, in addition to these questionnaire data, they also collected a biomarker of tobacco smoke exposure on individuals between the ages of 3 and 150. For this one, they drew a blood sample and they measured the amount of cotinine in the serum. Cotinine was a continuous variable. Now, cotinine is a metabolite of nicotine. And so this is a very objective measure of the amount of exposure to tobacco smoke that has occurred recently. So these are the variables that I'm going to consider for use in my models. Now, I should note, when you go to the NHANES data to look for your own variables, you should remember a couple of things. One is that the exposure variable has to come from the same cycles of the data where you found your outcome variables. So for me, that is the 2007, 2008, 2009, and 2010 cycles. Now, the variables that I've shown here are included in those cycles, so they're going to be okay. The other thing that you need to remember is to pay attention to the sample sizes if you're going to be using a categorical variable. You want to remember that the smallest category in your categorical variable shouldn't have fewer than about 200 people in it. Now, before I go back to my data, I want to introduce a very important principle, and how well you handle this principle will have a big effect on the failure or the success of your model. The idea here is that you need to consider how your exposure and your effect play out in time in relationship to each other. Now let's look at a different type of study to illustrate this principle. This is a representation of what's called a time series analysis. This is different than the type of study that we're doing with the NHANES data, but we can illustrate the principle here, and it will also show that the basis of all of these different types of models is the same. We're looking for patterns in the data, and then if we find patterns in the data, we are hypothesizing a particular cause and effect relationship based upon those data. So here, the cause and effect relationship that we are hypothesizing is that when the amount of air pollution in a city goes up, the rate of mortality in the city will also go up. And so what we have represented here are, these are days. This is Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, etc. And what we have here on the top is a representation of what the air pollution is on each of those days. And down here we have the rate of mortality on each day. So if we move through each day, and down here on the bottom right corner, we look at the air pollution and daily mortality to see if we have any kind of pattern in the data, what we see here is that on some days the air pollution goes up, but the daily mortality doesn't. On other days, the daily mortality goes up, the air pollution doesn't. On some days, they go up together. So it seems on some days the variables are moving together, and on other days the variables are moving against each other. So there's no clear pattern in the data here. So if we were to look at the data in this way, we would conclude that there is no evidence of a causal association between air pollution levels and the rate of daily mortality. But what we should notice here is that actually what's happening is that when the air pollution level goes up on one day, the effect on the daily mortality doesn't happen for another 3 days. There's this 3-day delay between exposure and effect here. So that's the delay between the exposure and the effect. Now, another thing we should notice is, once the effect occurs, how long does it take for that effect to go away? So what we see here is that when the air pollution goes up, on the 3rd day after, the daily mortality goes up for 1 day. On the following day, it's still slightly elevated, but it's coming down. But by the next day, it's back to the original level. And so we see that this happens in each of the 3 events where the air pollution goes up. The pattern is the same. So if we were to look for patterns in this data, what we should be doing is we should be comparing the air pollution level on 1 day to the mortality rate 3 days later, as in this example. Now, when we look at the data in this way, let's see what happens down here in the right-hand corner. Now what we see is a clear pattern in the data. The variables are moving together, and based upon this pattern in the data, we would be able to conclude that we have evidence of a causal association between the level of air pollution and the rate of daily mortality. Okay, now let's take this principle of the delay and persistence of effects and apply it to my particular model that I'm trying to build. So here we have on the left, this represents the individuals who are in our data set. And now I've got tobacco smoke and FEV1 to FVC up here. But we don't have days down here. We're not going to be comparing tobacco smoke and FEV1 to FVC ratio on different days. What do we have down here? What we have down here are going to be the individuals that are in our data set. If you remember, before we were comparing the variables within individuals across the data set. So this is also incorrect up here. We shouldn't be looking at the tobacco smoke exposure of one individual compared to the FEV1 to FVC ratio of another individual. So our data would look like this. And if we look down here on the right, what we expect to see is that we expect to see the variable for tobacco smoke exposure to be moving in opposition to the variable for the FEV1 to FVC ratio. But the question is, how are we going to construct this tobacco smoke variable so that we see the appropriate relationship between the variables down here? And the answer is going to depend upon the particular phenomenon that you are trying to model. So you're going to have to go to the literature and learn about the natural history of the particular disease that you're looking at, in particular in relationship to the exposure that you're modeling. So when you're doing this, sometimes it's helpful to think about it in a particular way. Because if we think about our population of people, the people who are in our data set, and the people who are represented by our data set, we might realize that there are going to be different levels of susceptibility to the exposure that we're trying to model. For example, here, with my model, some people are going to be more resilient to the effects of tobacco smoke. And so the effects on their FEV1 to FVC ratio are going to be smaller, whereas other people are going to be more susceptible. They'll be quite sensitive, and so they'll have larger effects on their FEV1 to FVC ratio after being exposed to tobacco smoke. And remember that we have defined the causal effect here at the population level, not at the individual level. But when we're thinking about the natural history of a disease, it is easier for us in our minds to think about a single individual and their experience with the exposure and the outcome. And so what might be helpful at this step is to imagine a person who is more average in their susceptibility or their resilience to the particular exposure that you're looking at in relationship to your outcome. So, for example, I might think of someone who is not super sensitive to tobacco smoke, but who is also not super resilient. So to think about the delay and the persistence of the effects, we might think about a person who doesn't smoke and then think about a person who does smoke. So let's do that for my particular exposure and outcome. Now you may remember from the last video that we saw that for FEV1 to FVC, there is a natural decline in the measure with age. And this is considered just a natural part of aging. So if we think about the person who doesn't smoke, we might represent the natural history of their FEV1 to FVC by this yellow line. So what will the natural history of the FEV1 to FVC ratio look like for somebody who smokes? Now this information came from my literature review. So what appears to be true for my exposure and effect is that if you are a smoker, and this red line down here represents smoking from age 20 until age 80. And so what happens for a person who smokes over their lifetime? Their FEV1 to FVC ratio declines at a faster rate over their lifetime than would have been true had they not been a smoker. So how do we think about the delay between the exposure and the outcome here? The delay between exposure to tobacco smoke and decreases in the FEV1 to FVC ratio. Well, in this case, it seems that it's more a cumulative effect, that for every bit of tobacco smoke that you are exposed to, your FEV1 to FVC ratio is decreasing at a faster rate than it would have been had you not been exposed. Now, what about the persistence of the effect? In the time series analysis, we saw that when the air pollution went up, the mortality rate went up, but it came back down after about 2 days. So there the persistence of the effect was only about 2 days. And so that led us to construct our exposure and our outcome to be apart from each other by 2 days. But here the effect seems to be different than that, and it's seen by this blue line here, which represents someone who smoked from age 20 until age 65. And what appears to happen is that as the person is smoking, their FEV1 to FVC ratio is decreasing at the rate that is expected for an average smoker. But when they stop smoking, the rate of their FEV1 to FVC decrease goes back to what it would have been if they had not been a smoker. So this line is at the same slope as this line. But the thing to notice here is that the FEV1 to FVC ratio that they've lost because of their smoking never comes back. So the effect here is permanent. There is no getting back the FEV1 to FVC ratio that they have lost. So what we have here is a diagram of 3 people, and this is our concept of what an average person would look like under 3 different conditions. The yellow line is the condition if they were a non-smoker. The red line is a condition if they were a smoker from age 20 till 80. And the blue line is a condition if they were a smoker from age 20 till 65, and then they stopped smoking. Now, another thing to recognize here is that we're looking at our concept of what happens in response to the exposure over the entire lifetime of an individual. But our data are cross-sectional, so the data are collected on each person who's in the data set at one particular time. We only see a snapshot of their life at one particular time. And so the situation would be different if the data were collected on these individuals when they were 50 years old compared to if the data were collected when they were 75 years old. All of them have a lower FEV1 to FVC at age 75 compared to 50. But what else do we notice? We notice that at age 50, the person who quits smoking at age 65, they have the same FEV1 to FVC ratio as the person who smokes until they're 80. Well, of course, that's because this person here who's represented by the blue line hasn't stopped smoking yet. But if we collect the data out here at age 75, then the person on the blue line, since they've stopped smoking at age 65, they now have a higher FEV1 to FVC ratio than the individual who continued smoking. So how do you think we should construct the exposure variable here? Well, one thing we can notice is that why is it that these 2 individuals, the one represented by blue and the one represented by red, have the same FEV1 to FVC ratio at this point in time, but they don't have the same at this point in time? Isn't it because they have, at this first point of time, at age 50, they have the same exposure? Both of them have been smoking since they were age 20, and now they're age 50. But at this point in time, they have a different exposure because one of them stopped smoking at age 65, but the other continued smoking. So this should give us a clue about how we should construct the exposure variable. Isn't the exposure here the cumulative exposure, the total exposure to tobacco smoke over the lifetime? And so we should use as our exposure measure the length of time that somebody has been a smoker. So if the data were collected at age 50 on both of these individuals, they would both be coded as having an exposure of 30 years to tobacco smoke. And so that is why their FEV1 to FVC ratio would be expected to be the same at that point. But if the data were collected at age 75, this individual in the red would be coded as having had 55 years of exposure to tobacco smoke, whereas this person would only have an exposure of 45 years. The shorter exposure, the lower exposure, would be the reason that this individual in blue would be expected to have a higher FEV1 to FVC ratio at age 75 compared to this individual represented by red. Now, some of you may be feeling that this is getting a little bit difficult, and you're wondering how you're ever going to be able to think of this idea about how to construct an exposure variable by yourself. And I would say, don't worry about it at this time. We're going to bring your ideas to class about what cause and outcome you want to possibly model. And we'll have a chance to talk about it together and to think through how you should construct your variables. Now, one of the things I'm going to ask you to do is to conceptualize, if you could have any data at all, what your ideal exposure measure would be. And in thinking about mine, I realized that I've come to the idea that I want a measure of the cumulative tobacco smoke exposure that someone has experienced in their life. But the way I've been talking about it is as if active smoking is the only way that people are exposed. But in fact, that's not true, is that people are exposed to tobacco smoke through passive smoking. And the other thing I notice is that I've conceptualized active smoking as if it's a kind of constant activity over an individual's lifetime. But we know that's not true. People smoke more and less. When they get under stress, they smoke more. They try to cut back, so they smoke less, and then they go back to smoking more. So the amount that somebody smokes is not constant over their lifetime. So for that reason, a measure of how long someone has smoked is not exactly going to get at how much tobacco smoke someone has been exposed to in their lifetime. So what would be my ideal exposure measure if I could have anything that I wanted? And I think for me it would be, I would want to know the mass in grams, how much tobacco smoke has entered into somebody's lungs during their lifetime, whether from active cigarette smoking, from secondhand smoke exposure, from cigarettes, from pipes, from cigars. This would be the ideal exposure measure for this model, where I want to find a pattern with the variable in relationship to the FEV1 to FVC ratio. Now, the reason I want you to conceptualize your ideal exposure measure is because you can then use that and go to the NHANES data to see how closely you can represent your ideal. Now, you're never probably going to be able to actually have the ideal measure that you want. And so you're going to be using a kind of proxy for that ideal measure. And the question you're going to have to ask yourself is, are the data that are available in the NHANES good enough to represent what it is that you're trying to represent? Now, this is one of the differences between doing primary research and secondary research. In primary research, you're designing your questions before you design the study. And so you can go out and you can collect the data that you need to answer the specific questions that you want to ask. But we're doing secondary research, which means that we're using existing data. And so we have to match the questions we ask with the data that are available to us. Now, you might find that the cause and outcome that you want to model just can't be modeled well using these data. And if you find out that that's true, then you're going to have to think of a different cause and outcome to model using the data. So with this in mind, let's go look again at the variables that I found were available in the NHANES data for my model. If we look again at the variables, we have you smoked at least 100 cigarettes in your entire lifetime? I can use this variable to classify people who were never smokers. If someone has never smoked more than 100 cigarettes in their entire lifetime, I'll probably just consider them a never smoker. Now, the second question is for people who ever smoked fairly regularly in their life. It asks them how old they were when they first started. So this will be the starting point for their exposure to fairly regular smoking. Now, the third question asks them if they're still smoking. Now, if they're still smoking, I will just consider that they are still fairly regular in their smoking. And so their cumulative exposure to fairly regular smoking will be the difference in their ages when they started and their current age at the time of the survey. Now, for those people who are not smoking cigarettes, the fourth question asks them how old they were when they stopped smoking fairly regularly. And so their cumulative exposure to fairly regular smoking will be the difference in the ages when they started smoking fairly regularly and the age when they stopped. So this construct of my exposure is very similar to my original idea about the smoking variable that we saw earlier. It's a measurement of the amount of time that someone smoked fairly regularly. So now is when I have to consider whether this kind of exposure construct is good enough relative to my ideal exposure construct. And you'll remember that my ideal idea about the exposure measure that I would want to have would be the cumulative mass in grams of tobacco smoke exposure that someone had over their entire lifetime from all sources. So what's the difference between that and what I'm able to get from the NHANES data? Well, I see a number of limitations. One is that the term fairly regularly, when they ask when did you start smoking fairly regularly, is somewhat vague. And so probably different people are going to interpret that term differently. And so we're going to be measuring slightly different things for different people. So this is going to introduce a little bit of measurement error into the construct. Another limitation is that we're depending on people to remember accurately when they started and stopped smoking fairly regularly. It's almost certain that people will make some errors in this. And so this is also going to introduce some measurement error into the construct. Now, a third issue relative to my ideal is that this construct only gets at active smoking. It doesn't have any information about secondhand smoke exposure. Another issue is that some people will have quit smoking multiple times during their life. But the questionnaire only asks them their age at the last time that they quit smoking fairly regularly. And so all of those multiple gaps when they weren't smoking before are going to be counted as time that they were actually smoking. So again, this is going to introduce some measurement error into the construct. And finally, there's no information about the magnitude of smoking, only the amount of time that they spent smoking fairly regularly. And so someone who smoked very heavily for 10 years is going to be coded as having the same exposure as someone who smoked fairly regularly for 10 years, but at a much lower magnitude. So I have to ask myself, is this good enough for me? Now, I think for the purposes of this class, this will be good enough. Although I would say that this is not an ideal model. This kind of model might be appropriate if I was doing some sort of exploratory analysis. Sometimes in an early field of study, we will do models that have more error in them. And if we see some evidence of a cause and effect relationship, we will go and design a new study to collect data with less measurement error. Now, one of the reasons I think this might work is because I expect smoking to have a strong effect on the airway constriction and COPD. And the years of exposure are probably going to be fairly large here for a lot of people in the population. So you can think a year of smoking fairly regularly, that's a really big exposure. And I think the magnitude of exposure of active smokers over multiple years is going to be so large relative to the errors that come from vague terms, recall errors, and lack of secondhand smoke, lack of measurement of multiple periods of quitting, and the magnitude of smoking, that those measurement errors are going to put an acceptably small amount of bias into this model. And again, this is for learning. And so having some information error in the model is not a bad thing because it will give us an opportunity to include that in our interpretation of the uncertainty of the model. Now, you may be wondering why I'm not considering using serum cotinine as my exposure measure. Serum cotinine gets at passive smoke exposure, and it doesn't have the problem that comes from recall errors in a questionnaire. But the issue with serum cotinine is that it has a half-life in serum of only about 15 to 20 hours. Now that's a long enough half-life to make its concentration in serum fairly stable throughout the day. And that's why it's the preferred measure of passive smoke exposure in this kind of study. But because of its half-life, it can only be considered to represent recent exposure. And as we saw earlier, because of the delay after exposure and the persistence of the effect, we need a construct of exposure that is cumulative rather than the recent exposure to tobacco smoke. And so serum cotinine is really not suitable for this model. So a mistake that people sometimes make is to think that because biomarkers such as cotinine are objective measures, that they are always the best choice in a research study if they are available. But what we can see here is that's not true. And I'd just like to take a moment to look at this a little bit more carefully. Let's think about if we use cotinine as the measure of tobacco smoke exposure in our model with COPD. Cotinine is measuring recent exposure to tobacco smoke. But think about it for a moment. If everyone in the United States population had COPD, compared to if everyone in the United States population didn't have COPD, in which situation do you think that the prevalence of active smoking would be higher? Well, probably if everyone had COPD in the United States, then the prevalence of smoking would actually go down. When people get COPD, they tend to stop smoking. And so if we did a model of cotinine and COPD, what we would likely find is that those who have COPD have actually lower levels of cotinine. Not only are they not smoking, but the people around them who smoke will go outside to avoid exposing them to their tobacco smoke. So you remember, when we see a pattern in the data between two variables, there are three possibilities for the causal structures that account for those patterns. In this case, one would be that smoking is causing COPD. Another one is that COPD is causing smoking. And a third one is that there's confounding. Now, in this case, if we use cotinine, if we found that those who have higher cotinine actually have lower prevalence of COPD, what we actually would be picking up is the second causal structure. It's the COPD that's having a causal effect on the smoking. It's because people who get COPD stop smoking. So COPD actually has a causal effect on the smoking. If we were to use cotinine and try to interpret it using the first causal structure, that smoking causes COPD, then we would conclude that smoking is actually protective for COPD. But of course, this is nonsense. So this should really drive home the point that a biomarker of exposure, although it has many advantages, is maybe not the best measure for every particular study. It really depends upon the delay after exposure of the effect and also the persistence of the effect once the exposure is taken away. In addition to that, it depends upon the half-life of the biomarker. Does the biomarker represent long-term exposure, or does it only represent recent exposure? Now, if I was looking at a different outcome in relationship to tobacco smoke exposure, say something like cough and wheeze. Now, cough and wheeze, if you remove the exposure of tobacco smoke, the risk of cough and wheeze is probably going to go down as well. And so unlike airway constriction, which is a persistent effect, the effects of cough and wheeze are less persistent. So for something like that, actually cotinine might be a very good measure. Because for cough and wheeze, what you actually want is a more recent exposure. Because an exposure that happened farther back in time is actually not going to have any more effect on the risk of cough and wheeze. The overall point here is that you need to consider how the exposure and the outcome act through time for a person in the population who has average susceptibility to the exposure. Okay, so I've chosen the causes and outcomes for two different models, and I'm going to be taking my data from the 2007 and 8 and the 2009 and 10 cycles. And for both models, my causes or exposure variables are going to be the same. They're going to be tobacco smoke exposure. And I'll have two different outcomes. In one model, I will be looking at airway constriction as the outcome, which will be a continuous variable. And in the other model, I'll be looking at COPD, which is a binary variable. Now, one thing I should note is that although the spirometry data were collected on individuals ages 6 to 79, the questionnaire data that I will be using for smoking was only collected on individuals aged 20 to 79. So I will be limiting my models to individuals who are between the ages of 20 and 79. Okay, so you should be ready now to go to the NHANES data and begin looking for the cause and outcome that you want to choose for your model. So good luck and have fun and bring your questions to class.